So think about this. You break your arm, you go to the hospital, and, the doctor puts you in front of an X-ray machine.
Right, pretty standard.
Yeah. A few minutes later, you've got that image on the screen, and the doctor points to this jagged white line. They tell you exactly what's broken, how to set it, and, exactly how long it'll take to heal.
It's an incredibly precise, mechanical way to look at the human body.
Exactly. We expect that level of precision in medicine. But today, we're actually flipping that perspective.
Oh, totally. We're looking at the engineering of actual metal arms with that exact same level of anatomical precision.
Right. And you, the listener, you're in high school right now. Maybe you're staring down an engineering track for college, or I don't know, maybe you're just intensely curious about the hidden machines that actually manufacture the modern world around you.
Because when you picture a robot, it's almost definitely a Hollywood creation, right?
Oh, 100%.
Oh.
A metallic humanoid wandering around a spaceship, or some rogue AI taking over a city.
Yeah, forget the sci-fi movies. Just put them completely out of your mind.
Today, we are exploring the real mechanical muscles and, frankly, the heavy mathematical brains of actual industrial robots.
It is so vital to strip away that Hollywood veneer. The reality of robotics is far more grounded than a walking android. But structurally, it is infinitely more fascinating.
Yeah, I mean, we gravitate toward humanoid robots in fiction because we are human. We want to relate to things that look like us.
Exactly. But the actual landscape of industrial robotics, the machines building our cars, our phones, our computers, they operate on an entirely different set of physical and mathematical rules.
It's an absolute engineering marvel. Yeah. So our mission for this deep dive is to act as your translators for what I'd consider the ultimate blueprint of these machines.
Which brings us to our primary source today.
Right. It's a dense university-level text called Fundamentals of Robotics, Analysis and Control by Robert J. Shilling.
It's the kind of textbook that can look really intimidating. It's filled with advanced calculus and, dense diagrams.
Yeah, but we are going to decode it, so you don't need a PhD to get it. We're going to mentally build a robot from the factory floor up.
We'll look at the massive financial reasons they exist, how their metallic muscles and bones physically actuate, and the invisible 3D shapes they carve into the air.
And, of course, the complex high school math that makes every single movement possible.
Setting a strict dress line is the only way to begin. In the opening chapter, Shilling tackles that sci-fi misconception head-on.
He does. He actually brings up Isaac Asimov's classic 1950s science fiction.
Right, noting that the popular notion of an android built to impersonate human wandering is totally divorced from industrial reality.
I mean, most modern robots don't even have the capability to move from one place to another. They are literally bolted firmly to a concrete floor.
Yeah. So we should look at the textbook's explicit definition here because it really sets the stage.
Let me grab that. Okay, it's labeled Definition 111. It states, a robot is a software-controllable mechanical device that uses sensors to guide one or more end effectors through programmed motions in a workspace in order to manipulate physical objects.
Let's pull that apart because on the surface, it sounds like a description of, your garage door opener.
Yeah, it really does. But a garage door opener lacks the most critical elements of that definition.
Exactly. Let's look at software controllable. A garage door just runs a motor until a physical switch tells it to stop.
Right, it's just on or off.
But a robot's physical actions are continuously dictated and updated by complex code. That gives it extreme flexibility.
And then you have sensors. The robot is actively receiving feedback about its environment.
Right, like where its joints are, how fast they're moving, sometimes even what it's touching.
And then there's this great piece of engineering jargon, the end effector.
Such a great term.
It is. Which is really just a fancy clinical way of saying the hand or the tool at the very end of the arm. It's the part that actually interacts with the physical objects.
The most crucial takeaway from Schilling's definition, though, is the limitation of how human-like these machines are.
Yeah, the text points out these machines are only anthropomorphic in a very specific structural way.
Right. They're patterned after the human arm, not the whole human body. They possess mechanical joints that correspond to a shoulder, an elbow, and a wrist.
Which means calling them robots, with all the baggage that word carries, is almost a misnomer.
The textbook clarifies they are more properly called robotic manipulators or robotic arms.
We are literally talking about massive, incredibly precise, disembodied arms.
It's a bit creepy when you think about it like that.
It really is. But before we figure out how to bolt one together, there's a glaring economic question, like, why build them at all?
Money, usually.
Right. If I'm running a factory, my goal is to make my product as cheaply and reliably as possible. Human beings are incredibly dexterous, and simple machines are incredibly fast. Why spend millions on these complex robotic arms?
To understand the economic incentive, Shilling actually takes us back to 1905.
Ooh, the Henry Ford era.
Exactly. Think about the Ford Motor Company and the birth of the mass production assembly line. Over the next several decades, industrial engineers perfected what is known as hard automation.
Hard automation. So these were highly specialized, custom-built machines designed for the high-volume production of very specific mechanical parts.
Spot on.
I think of hard automation like this. Imagine you're running a commercial bakery, and your signature item is a chocolate chip cookie.
Okay, I'm with you.
You hire an engineer to build a massive multi-million-dollar machine. It mixes the dough with the exact required torque, drops perfectly measured portions onto a conveyor belt, and bakes them at a precise temperature.
A masterpiece of efficiency.
Right. It cranks out 10,000 identical chocolate chip cookies an hour. But what happens 6 months later when consumer tastes change and suddenly everyone wants oatmeal raisin?
Well, your $1 million machine only knows how to drop chocolate chips.
Exactly. My machine is useless.
That vulnerability is the absolute Achilles heel of hard automation.
Because you can't just tell it to do something else.
No, Schilling explains that when a production cycle ends, say, a car manufacturer is transitioning from the 2025 model to the completely redesigned 2026 model, those specialized hard automation machines cannot adapt.
The hardware itself is entirely rigid.
Yeah. The factory has to be completely shut down. The machines must be physically disassembled, redesigned, and retooled for the new parts.
That sounds like a logistical nightmare. You have a factory the size of 3 football fields sitting completely idle, generating zero revenue.
All while teams of mechanics spend months swapping out custom metal parts just so you can start making the new car door.
It has to be exceptionally expensive and time-consuming. Hard automation offers peak efficiency for unchanged products, but zero flexibility.
Right. The manufacturing world needed a solution that provided the tireless speed of a machine, but the adaptable nature of a human worker.
And that gap in the market gave birth to soft automation.
Exactly, which is the robotic manipulator. Because instead of changing the physical hardware, swapping out gears and levers, you just change the code.
They're defined in the text as programmable mechanical manipulators.
Yeah, a single robotic arm might spend the morning doing spot welding on a truck frame.
And then in the afternoon, you load a different software program, swap the end effector from a welder to a spray gun, and it's painting the truck.
You don't rebuild the machine, you just change its mathematical instructions.
But if they are that flexible, it begs the question, why isn't everything soft automation? Why do factories use humans or hard automation at all?
It comes down to a very specific calculation of production volume versus cost.
The break-even point.
Yeah, the textbook provides a fascinating graph, figure 1-2, that illustrates the relative cost-effectiveness of manual labor, hard automation, and soft automation.
Let's visualize this graph for the listener. If I'm looking at it, the bottom horizontal axis represents how many items I'm making.
Right, from one single item all the way up to 10 million.
And the vertical axis is how much it costs me to make each one of those items.
So if you look at the far left of the graph, the zone of small batch processing, human manual labor is the clear winner.
Because if you're only making 50 custom metal brackets, it makes zero financial sense to buy a $100,000 robotic arm.
Exactly. Plus hiring a programmer and building a safety enclosure. A skilled human machinist can adapt instantly to the blueprints and produce the batch far more cheaply.
That makes perfect sense. The human brain is the ultimate soft automation for tiny volumes. We require zero programming time. We just look at the drawing and do it.
But what about the far right side of the graph? The absolute massive volume.
For virtually infinite volumes of a product that will never ever change its design, hard automation is the cheapest option per unit.
Yeah, even though the initial custom machine costs a fortune, you spread that cost over hundreds of millions of units.
And the machine runs faster than any adaptable robot ever could because it was designed to do only one precise motion.
So where is the robot's territory?
Robots dominate the expanding middle ground. The graph shows a specific intersection, point V1.
This is the production volume where human labor becomes too slow and expensive to keep up.
And the robotic arm becomes the most cost-effective solution. As volume increases further, you eventually hit point V2.
That's the threshold where the sheer scale justifies spending the money to build a custom hard automation machine.
The space between V1 and V2 is the sweet spot for soft automation. It's perfect for medium to high volume manufacturing, where you know the product design will eventually evolve.
Like next year's smartphone or car model.
Right. And what's really interesting is that this sweet spot is actively growing. As robots get cheaper to manufacture and their software gets easier to program, that V1 point pushes further left.
It becomes cost-effective to use a robot for smaller and smaller batches.
Meanwhile, as robots get faster, the V2 point pushes to the right, eating into the territory of hard automation.
Exactly, the dynamic Shilling highlights. The economics demand programmable arms.
But knowing why we need them is only the prologue.
Right, the engineering challenge is how to build an arm that can manipulate a 1,000-kilogram engine block with grace, or pick up a delicate microchip without shattering it.
We have to look at the physical anatomy of the robot, starting with its drives, the mechanical muscles in its joints, the bones.
Let's focus on the muscles first.
How do we generate the raw physical force required to move these heavy steel arms? I assume there's more than one way to flex a robotic bicep.
The text outlines 3 primary drive technologies: electric, hydraulic, and pneumatic.
Okay, so 3 options.
Right. The vast majority of robotic manipulators today utilize electric drives. Shilling specifically points to DC servo motors, or DC stepper motors.
Those use electromagnetic fields to create precise rotational force, right?
Exactly. Electric motors make sense. They are clean, they plug right into the factory's power grid, and they can be incredibly precise.
I like to think of the electric drive as an elite gymnast. Very precise, very fast, highly controlled, and handles the vast majority of standard manufacturing tasks.
That's a great analogy, but the textbook also details hydraulic drives.
Now, why on earth would we use pressurized fluids to move an arm?
It is entirely about power density. Hydraulic systems use pressurized liquid, typically a specialized oil, pumped through hoses into cylinders.
Because liquids are virtually incompressible, right?
Right. You can transmit an astonishing amount of force through a relatively small tube. Shilling specifies that hydraulic drives are the preferred choice when the robot must manipulate substantial loads.
So if the electric motor is the gymnast, the hydraulic drive is the world's strongest man competitor pulling a semi-truck.
The examples in the text reflect exactly that scale. Hydraulic robots are used for handling molten steel crucibles in foundries.
Oh, wow. Or physically lifting and manipulating entire automobile bodies during the welding process.
An electric motor capable of generating that much raw torque would be massive, heavy, and incredibly inefficient. The hydraulic cylinder can be relatively compact while delivering immense power.
There has to be a trade-off, though. If hydraulics are so powerful and compact, why aren't they used for everything?
Fluid dynamics comes with a significant mechanical drawback. The text explicitly points out that hydraulic drive robots suffer from a lack of cleanliness.
They leak.
They require an extensive network of pumps, valves, high-pressure hoses, and seals. Over time, under immense pressure, those seals degrade.
And they run a very high risk of leaking hydraulic fluid. In a foundry, a few drops of oil on the floor might not matter.
But in a modern clean room assembling silicon wafers or a facility packaging food products,
A single drop of hydraulic oil ruins the product and stops the entire production line.
exactly, so you keep the heavy lifters out of the clean rooms.
That leaves us with the third type of drive mentioned, pneumatic tools.
Pneumatics use compressed air instead of pressurized liquid.
Where do we use air? I can't imagine airlifting a car chassis.
You're right, they are rarely used to move the heavy major axes of the arm itself. Instead, they are frequently utilized for the end effectors, the grippers or hands at the end of the robot.
Why air for the hands?
The fundamental difference between air and hydraulic oil is that air is a compressible fluid.
Compressibility. This is a huge concept.
Right. If I fill a syringe with water, plug the end, and push the plunger, it won't budge. The water won't compress.
But if I fill that same syringe with air, plug the end, and push, I can squish the air down significantly before the pressure stops me.
That physical property gives pneumatic tools a built-in characteristic that the text refers to as compliance.
Compliance, meaning it gives a little.
Yes. When a rigid electric motor drives a mechanical gripper to close on an object, it will blindly close to its programmed mathematical position.
If the object is slightly larger than expected or exceptionally delicate, that rigid electric motor will just crush it.
It's the difference between picking up a raw egg with heavy steel pliers versus picking it up while wearing incredibly thick, puffy winter gloves.
Oh, I love that. The pneumatic gripper acts like those puffy gloves. As the pneumatic hand closes around the delicate part, the compressed air physically squishes and acts like a built-in shock absorber.
It conforms to the object without applying crushing force.
It's an elegant physical solution to a complex sensing problem. Instead of writing thousands of lines of code and installing expensive pressure sensors to ensure the electric motor doesn't squeeze too hard.
You simply use the natural physics of compressed air to provide that selective compliance.
All right, we've got our electric gymnasts, our hydraulic power lifters, and our pneumatic shock absorbers. We have the muscles.
Now we need the bones.
How do the individual segments of this robotic arm physically connect and articulate?
Well, in robotics kinematics, the solid segments of the arm are called links, and the points where they connect are called joints.
Human joints, like the shoulder, are incredibly mechanically complex. I mean, they're capable of moving in multiple planes simultaneously.
Industrial robotics dramatically simplifies this. The textbook models robotic joints into two fundamental, easily mathematically definable types.
Okay, what's the first one?
The first is the revolute joint, which is denoted in the shorthand by the letter R.
Revolute. So it revolves. This is a hinge.
Yes. If you bend your elbow, or tilt your head up and down, or open a door, that is a revolute motion.
It is purely rotational motion around a single central axis.
Revolute joints are the most common in modern robotics. The second fundamental type is the prismatic joint, denoted by the letter P.
Prismatic?
Yeah.
How does that work?
Unlike the revolute joint, a prismatic joint exhibits purely sliding or linear motion along an axis. There is no rotation whatsoever.
So instead of a hinge, think of a trombone slide, or the telescoping legs of a camera tripod.
Or even just a drawer pulling out of a desk. It extends and retracts in a perfectly straight line.
Armed with just those two concepts, the revolving R and the sliding P, you can look at almost any complex machine around you and break its motion down into a sequence of hinges and slides.
And it is the specific sequence of those R and P joints, bolted end to end, that dictates the entire physical capability of the robot.
The arrangement determines the robot's work envelope, which introduces a massive concept from the text, the geometry of work.
Because if I am installing a multi-million-dollar robot in my factory, I need to know exactly how far it can reach.
Right. I need to know if it can reach the conveyor belt on its left, the welding station in front of it, and the tool rack behind it.
Exactly. The textbook defines the work envelope as the three-dimensional space that can be reached by the wrist of the robot.
Picture an invisible 3D geometric boundary hovering in the air around the machine. If an object is inside that boundary, the robot can touch it.
If it is a millimeter outside that boundary, it is physically impossible for the robot to reach it without moving its bolted base.
To understand how these envelopes are shaped, the text makes a really crucial distinction between the major axis and the minor axis of the arm.
A standard industrial robot often has 6 joints in total. The first 3 joints, starting from the heavy base bolted to the floor, are the major axis.
And their primary mathematical purpose is to determine the position of the wrist in 3D space. They do the gross physical movement.
They get the hand to the right zip code.
The remaining joints, usually 3 smaller joints comprising the wrist itself, are the minor axis.
Their job is not to move the hand through space, but to establish the orientation of the tool once it is there.
The major axes move the hand to the cup of coffee. The minor axes decide if you are grabbing the cup from the top, the side, or underneath.
Because those first 3 major axes determine the vast overall reach of the machine, engineers use them to classify the fundamental geometry of the entire robot.
Shilling provides Table 1-2, which lists 5 primary robotic classifications based solely on whether those first 3 joints are prismatic or revolute.
Let's walk through the geometry of these configurations. The first is the Cartesian robot. Its kinematic notation is PPP.
That means the first 3 major joints are all prismatic sliding joints.
3 slides.
If I slide left to right, that's an x-axis, then forward and back, a y-axis, and then up and down, a z-axis, the outer boundary my reach creates a perfect, massive rectangular box.
The work envelope is a pure rectangular prism.
The textbook notes that when this PPP configuration is suspended from a rigid overhead rectangular frame, it is referred to as a gantry robot.
Because they are built on rigid, straight tracks, they are incredibly strong and stable.
You see massive versions of these at shipping ports moving cargo containers and miniature versions inside desktop 3D printers.
A box is highly predictable. But what happens if we replace that first sliding track with a rotating base?
We change the configuration from PPP to RPP, 1 revolute to prismatic.
The textbook calls this the cylindrical robot.
Picture a heavy vertical pole. The base joint is revolute, so the entire arm swings in a circle around that pole.
The next joint is prismatic, allowing the arm to slide vertically up and down the pole.
The third joint is also prismatic, allowing the arm to extend outward horizontally.
If you trace the maximum reach of that arm as it swings around, reaches all the way up and extends all the way out, you draw the volume between two concentric vertical cylinders in the air.
It's perfect for reaching into a round kiln or moving parts between circular workstations positioned around the robot.
Now let's substitute one more sliding joint for a rotating one. We move to an RRP configuration. Two revolute joints, one prismatic.
This is the spherical robot. 2 hinges, 1 slide.
The base joint revolves horizontally. The second revolute joint acts like a shoulder, pitching the entire arm up and down.
The third joint is prismatic, acting as a telescoping boom that slides in and out.
The text describes its work envelope as the volume between two concentric spheres, though in reality, physical and mechanical limits usually cut off the very top and bottom, creating a truncated sphere.
I always picture a spherical robot like a heavy tank turret. The turret spins around, the cannon barrel pitches up and down, and then imagine the barrel itself can telescope outward.
That is your RRP spherical geometry.
Now, what if we abandon the sliding prismatic joints entirely? What if all 3 major axes are revolute? RR.
This is the articulated robot. It is the design most frequently used in modern manufacturing, and it is the most anthropomorphic because it mirrors human biology.
You have a resolving base, like a twisting waist, a shoulder joint that pitches, and an elbow joint that also pitches.
Listeners, try this right now to understand the articulation. Keep your arm perfectly straight, lock your elbow, and swing your arm from your shoulder.
You are mimicking a spherical work envelope.
Now bend your elbow. Suddenly you can reach back towards your own face. You can reach over an obstacle to grab something behind it.
You have become an articulated robot.
The ability to reach around and over obstacles makes the articulated arm incredibly versatile.
The textbook notes that the complex combination of these 3 rotations creates a work envelope with a very distinct crescent-shaped cross-section.
There is one final classification in Shilling's table, and it is so unique it gets its own acronym. The SCARA robot. SCARA.
It stands for Selective Compliance Assembly Robot Arm. It is technically an RRP configuration, 2 revolute, 1 prismatic, but it behaves entirely differently than the spherical robot we just talked about.
Why does the SCARA get special treatment?
It's about the specific alignment of the axis. In a spherical robot, the shoulder pitches up and down vertically.
In a SCARA robot, the first 2 revolute joints swing in a purely horizontal plane. The textbook uses a famous commercial robot, the Adept one, as the prime example of this kinematic arrangement.
To visualize SCARA, imagine resting your entire arm flat on a tabletop. You can bend your elbow, and you can swing your shoulder, but your arm remains perfectly flat and parallel to the table.
You are sweeping horizontally. The horizontal sweep handles the X and Y positioning.
Then the third joint, the prismatic one, is mounted at the very end of the arm, pointing straight down. It simply slides the wrist vertically along the Z-axis.
This very specific geometry was invented to solve a massive problem in the electronics industry, inserting incredibly delicate pins into printed circuit boards at high speeds.
This is where that phrase selective compliance becomes genius. If you are a robot trying to shove a metal pin into a tiny hole on a motherboard, and you are off by a fraction of a millimeter,
a rigid robot will just smash the pin, destroying the board.
Exactly the problem the engineers faced. The SCARA solves this mechanically without requiring complex software.
Because the arm only slides up and down on a rigid vertical track, it is incredibly stiff in the vertical direction. It can apply significant downward insertion force.
But because the shoulder and elbow joints swing freely in the horizontal plane, the arm possesses a tiny amount of natural physical give or compliance horizontally.
So if the robot comes down and the pin is slightly misaligned, hitting the chamfered edge of the hole, that horizontal give allows the arm to naturally deflect just a microscopic amount.
The pin slides smoothly into the hole instead of buckling. It's selectively compliant, rigid vertically, flexible horizontally.
It is a brilliantly simple kinematic design that revolutionized high-speed assembly.
We have now defined the physical hardware, the power, the joints, and the shapes they can reach.
But having a powerful, flexible arm is useless without a brain to orchestrate the movement.
Right. How does the computer actually control the trajectory, and how much can we actually trust its accuracy? Let's explore the illusion of robotic perfection.
When you watch a video of a car assembly line, the robots look absolutely flawless, repeating the exact same graceful dance endlessly.
But engineering is never about perfection. It's about mathematically managing real-world errors. The textbook starts this discussion by contrasting the two fundamental methods of motion control.
Point-to-point motion versus continuous path motion.
Point-to-point, or PTP motion, is conceptually straightforward. The user programs a sequence of specific, discrete points in the 3D workspace.
The control system is instructed to move the end effector from point A to point B. The crucial factor here is that the user does not explicitly dictate the exact path the arm takes between those points.
I program the destination, and the robot's computer figures out the fastest, most efficient way to get there. The exact arc it swings through the air doesn't matter.
The textbook notes this is standard for tasks like spot welding. The robot needs to pinch the metal at an exact coordinate and apply a weld.
It doesn't matter how the arm dances through the air to reach that coordinate, as long as it gets there quickly and doesn't hit a wall.
But many industrial applications demand total control over the entire trajectory. That is continuous path motion.
The text defines this as a control scheme where the end effector must follow a strictly prescribed three-dimensional path, often with strictly prescribed variations in speed along that path.
Now, mathematically speaking, isn't a continuous path just a computer stringing together thousands of tiny point-to-point movements?
Like playing connect the dots on a microscopic scale.
At the level of the microprocessor, yes, it is calculating discrete intervals. But mechanically and control-wise, it is vastly more complicated.
The controller must simultaneously interpolate the positions and velocities of every single joint in real time to ensure the tooltip never deviates from the invisible line drawn in the air.
The textbook uses spray painting and arc welding as the prime examples for continuous path. And it makes perfect sense.
If you are spray painting a car door, the paint gun is constantly spraying. If the robot hesitates for a tenth of a second, or if the path wiggles even slightly between calculated points,
You get a massive visible drip of paint on the car.
if you are arc welding a seam on a pressure vessel, a momentary stutter in speed creates an uneven weld that could literally cause the tank to explode.
The speed and the physical trajectory must be mathematically synchronized at every millisecond.
To achieve that level of synchronization, we have to talk about how the robot understands its own positioning.
Which leads to the three most misunderstood specifications in robotics, which Shilling meticulously defines: precision, repeatability, and accuracy.
In casual conversation, we treat these words as synonyms. In robotics, confusing them will cause catastrophic engineering failures.
Let's break down the big three. I think the classic dartboard analogy is the best way to visualize this.
Let's start with precision. The textbook formally defines precision as a measure of the spatial resolution with which the tool could be positioned within the work envelope.
When I read spatial resolution, I think of the pixels on a television screen.
That is an excellent way to visualize it. Imagine the robot's entire work envelope is not empty space, but a dense, invisible 3D grid made of millions of tiny dots.
The robot's control system and its digital encoders can only direct the arm to land exactly on one of those dots. It is mathematically and physically impossible for the robot to stop in the empty space between the dots.
So precision is simply a measurement of the distance between those tiny dots. The smaller the distance between the dots, the higher the precision of the robot.
In the dartboard analogy, precision is how sharp the physical tip of your dart is. A blunt dart covers a wide area on the board. A needle-sharp dart can pinpoint a microscopic fiber of the board.
But Shilling points out a fascinating geometric quirk about this invisible grid. The dots aren't always evenly spaced.
This is a profound realization about robotic geometry. For a Cartesian robot, the one built of 3 sliding tracks, the grid is perfectly uniform.
Moving 1 millimeter on the x-axis is the exact same amount of physical movement everywhere inside that rectangular box. The precision is constant.
But for an articulated robot, the swinging arm with the revolute joints, the precision physically warps depending on how far the arm is reaching.
Because revolute joints operate on angles. Let's use your own arm again. Tuck your elbow tightly against your ribs and move your shoulder by exactly 1 degree.
Your hand barely moves a fraction of an inch. The grid dots are very close together. Your precision is high.
Now, extend your arm completely straight out, locking your elbow so your hand is 3 feet away from your body.
If you move your shoulder by that exact same 1 degree, your hand sweeps through the air across a much larger distance. The angle is the same, but the arc length is huge.
The textbook highlights this geometric reality. For an articulated robot, Precision is highest along the inside surface of the work envelope, close to the base, and degrades significantly as the arm extends toward the outer boundary.
The dots on the grid physically spread further apart the further you reach.
Okay, so precision is the sharpness of the dart, the grid resolution. Next is repeatability.
Shilling defines this as a measure of the ability of the robot to position the tooltip in the same place repeatedly.
Imagine you program the robot to travel to a specific, highly precise dot on its grid. You run the program, it hits the dot.
Now you tell the robot to return to that exact same coordinate 10,000 times in a row over a 24-hour shift. Does it hit the absolute exact microscopic center of that dot every single time?
The answer has to be no. The real world has physics.
Exactly. The textbook details several sources of repeatability error. First is gear backlash. No matter how perfectly manufactured, there must be a microscopic gap between the teeth of the metal gears driving the joints.
Otherwise, they would bind from friction. That tiny gap allows a fraction of a millimeter of physical wiggle room.
Then you have the flex of the metal links themselves. If the robot picks up a heavy payload, the massive steel arm actually bends downward slightly under the weight.
And what about temperature? If the robot runs for 24 hours, the electric motors get hot, the steel heats up, and thermal expansion means the arm is literally physically longer at the end of the shift than it was at the beginning.
All of these real-world physical factors mean that the tooltip will scatter slightly around the target coordinate.
Back to the dartboard. Repeatability is throwing a cluster of darts. You throw 20 darts and they all land in a tight half-inch grouping. The robot is highly repeatable.
But, and this is the absolute kicker, that incredibly tight cluster of highly repeatable darts might be stuck in the drywall 3 feet to the left of the dartboard.
Which brings us to the final and most brutal specification: accuracy.
Accuracy is the measure of whether the coordinate you programmed into the computer actually corresponds to that exact physical location in the real world.
If I type x equals 100 millimeters, y equals 100 millimeters, does the tooltip actually arrive exactly 100 millimeters from the base frame in the physical universe?
Throwing the dart and hitting the dead center of the bullseye, the textbook has a surprisingly sobering assessment here.
Shilling writes, although robotic manipulators are not nearly as accurate as their more expensive and specialized hard automation counterparts, they do provide increased flexibility. It is one of the great challenges of robotics to make use of this increased flexibility to compensate for less than perfect accuracy.
Wait, we are talking about machines that cost hundreds of thousands of dollars. Are they really not accurate?
It is the great open secret of industrial robotics. They are breathtakingly repeatable. They can execute the exact same slightly flawed movement flawlessly 10,000 times in a row.
But without external help, they can easily drift out of absolute accuracy. A robot is fundamentally blind.
If you program it to plunge a bolt into an engine block at coordinate XYZ, it will go to XYZ.
If the engine block on the conveyor belt was loaded slightly crooked by even 2 millimeters, the robot doesn't know.
It will blindly plunge the bolt, strip the threads, and destroy the engine block. The mathematics assume a perfectly rigid, predictable universe. The factory floor is anything but perfect.
Which is the perfect transition into the deepest part of the textbook. We've talked about the physics, the shapes, and the errors, but how does a computer actually calculate the movement?
Because the robotic hardware doesn't understand inches or millimeters, the motors only understand one thing: spin this many degrees.
Transforming a desired 3D coordinate into a specific set of motor angles is where high school math, trigonometry, algebra, and matrices turns into literal real-world magic.
The translation of coordinates to angles is the core of robotic programming. Shilling dedicates a massive portion of the text to what is formally called the kinematics problem.
Kinematics is a branch of physics that studies the geometry of motion without considering the forces or mass that cause the motion. We aren't calculating gravity or payload weights yet. We are purely calculating the geometric angles of the skeleton.
The text divides this entirely into two distinct problems: direct kinematics and inverse kinematics.
Let's start with direct kinematics. The textbook refers to this as developing the arm equation.
I look at it as a forward-moving logic puzzle. The concept is, if I know the angle of every single joint, where is the hand?
For example, if I bend my shoulder exactly 30 degrees, bend my elbow exactly 45 degrees, and twist my wrist 10 degrees, what are the final XYZ coordinates of my fingertips?
Precisely. You are given the specific joint variables, what the text called the joint space coordinates. and your goal is to calculate the tool configuration in the real world.
That configuration consists of the three position coordinates, x, y, z, and the three orientation coordinates, yaw, pitch, and roll.
How does the computer actually calculate that? If you have a six-jointed robot, the math must get incredibly tangled.
It relies heavily on a mathematical tool called a homogeneous transformation matrix.
A matrix is essentially just a grid of numbers arranged in rows and columns.
In robotics, engineers use a specific 4x4 matrix grid that simultaneously tells the computer two things: how far to translate or slide in a straight line, and how far to rotate or spin around an axis.
So instead of trying to calculate the massive, complex arc of the entire arm all at once, you break it down joint by joint.
You write a matrix for the shoulder, then you write a matrix for the elbow, then you write a matrix for the wrist.
And then you simply multiply those matrices together in sequence, starting from the fixed base of the robot and moving step by step down the kinematic chain out to the tooltip.
It is a highly systematic, algebraic process. You plug in the known joint angles, you crunch the multiplication, and the final resulting matrix tells you exactly where the tooltip is hovering in 3D space.
It's basically plug-and-chug math. If you know the angles, finding the position is a straightforward, guaranteed calculation.
But the textbook points out a massive practical problem. When I am standing on the factory floor programming a robot to pick up a spark plug, I don't think in joint angles.
I don't look at the spark plug and say, I need motor 1 to spin 32.5 degrees and motor 2 to spin 12 degrees.
I look at the spark plug and say, put your hand at coordinate x, y, z on the table.
And that reverse engineering is the inverse kinematics problem.
The inverse kinematics problem is the reality of robotic control. The logic is reversed. I know exactly where I want the hand to be and exactly what direction I want it pointing. Now, computer, calculate the specific degrees every single motor must turn to achieve that exact pose.
On the surface, that just sounds like doing the direct kinematics math backwards. Why does Shilling explicitly state that the inverse kinematics problem is infinitely more difficult to solve?
Because algebra behaves differently in reverse, especially when sines and cosines are involved. With direct kinematics, if you plug in the angles, there is only one possible physical location the hand can be. It's a unique solution.
With inverse kinematics, you are working backwards through complex nonlinear equations. There is rarely a single systematic mathematical procedure to solve it.
More importantly, the math often yields multiple, equally valid physical solutions.
Multiple solutions. You mean there is more than one way to reach the exact same point in space?
Let's use our bodies again to visualize this. Listeners, try this. Hold your hand out directly in front of your face and hold it completely still.
Your hand is now locked at a specific XYZ coordinate.
Now, without moving your hand, raise your elbow up toward the ceiling. Now, drop your elbow down toward the floor.
That is a perfect physical demonstration of kinematic multiplicity. Your hand, the end effector, remained at the exact desired mathematical coordinate.
But the angles of your shoulder and your elbow changed drastically. The textbook refers to this specific scenario as the elbow up versus elbow down configuration.
So the computer crunches the inverse kinematics equations, and the math spits out two completely different sets of motor angles that both achieve the goal. How does the robot know which one to choose?
That is the burden of the control software. It has to evaluate the multiple solutions based on physical constraints.
The elbow-up configuration might be mathematically valid, but physically, it might cause the elbow joint to smash into a safety railing on the factory floor.
Or it might require the shoulder motor to spin past its physical hardware limits. The software must calculate all solutions and select the one that is physically safe and mechanically optimal.
The textbook goes deep into the weeds on this, spending pages working through the inverse kinematics of a 5-axis educational robot called the Rhino XR3.
It shows the brutal algebraic manipulation required to isolate each specific joint angle.
But it also points out that sometimes the math doesn't yield multiple solutions. Sometimes it yields 0 solutions.
If you command the robot to reach a coordinate that is physically outside of its work envelope, asking a 5-foot arm to reach a point 10 feet away, the trigonometric equations literally break down.
You end up trying to calculate the inverse sine of a number greater than 1, which is mathematically impossible. The computer realizes the requested coordinate is an unreachable phantom.
That makes intuitive sense. You can't reach further than your arm is long.
But Shilling introduces a concept that completely blew my mind, where the math violently breaks down even when the hand is inside the safe work envelope. He calls them joint space singularities.
Singularities are the boogeymen of robotics control. They are mathematical black holes.
The formal definition in the text, definition 521, states that a joint space singularity occurs when the tool configuration Jacobian matrix loses rank.
Okay, stop right there. Jacobian matrix loses rank. When I read that, my eyes completely glazed over. Let's strip away the high-level calculus. What is a Jacobian matrix, and what physically happens to the massive steel arm when it loses rank?
Let's break it down. We already talked about matrices, grids of numbers that map position. A Jacobian matrix is a specific grid of numbers that map speed.
It translates the velocity of the individual spinning joints into the final linear speed of the tooltip moving through the air.
It is the mathematical bridge between rotational motor speed and straight-line hand speed.
So the control computer constantly calculates this Jacobian matrix to ensure the paint gun is moving at the exact right speed.
Exactly. Now, losing rank is a term from linear algebra. It happens when the rows or columns of that grid of numbers become linearly dependent.
Basically, when the math equations collapse in on themselves and become redundant. In a computer, this often results in a scenario where the algorithm attempts to divide by zero.
Divide by zero, the ultimate computer error. But what physical posture causes the arm's math to divide by zero?
Singularities typically occur in two specific physical scenarios. The first is a boundary singularity, which happens when the arm is stretched out completely straight, locking out to reach the absolute edge of its work envelope.
The second, more insidious type, is an interior singularity. This happens when two or more rotational joints physically line up so perfectly that their axes of rotation overlap.
When the joints line up perfectly, they suddenly operate on the exact same mathematical plane. In that exact moment, the robot mathematically and physically loses what engineers call a degree of freedom.
It temporarily loses the ability to move in one or more directions, no matter how hard the motors spin.
The physical reality is violent. If the robot is executing a continuous path movement like a straight line weld, and that path passes directly through a singularity.
The inverse Jacobian mathematics dictate that in order to maintain a constant tooltip speed, the joint velocities must approach infinity. The software commands the heavy steel motors to instantly spin infinitely fast.
The analogy I came up with for this loss of a degree of freedom is locking your knees. Imagine you are playing basketball. You are standing with your knees slightly bent in an athletic stance.
From that bent knee position, you can instantly jump, you can squat, you can lunge left or right, you have full mobility, you have all your degrees of freedom.
Now stand up straight and lock your knees perfectly rigid.
Your joints are completely aligned, their axes overlap.
If someone lightly pushes your shoulder while your knees are rigidly locked, you just fall over like a tree.
Because your joints were aligned, you lost the mechanical ability to quickly flex and step back to catch your balance. Your mobility plummeted to zero in that specific direction.
A very apt physical analogy. A robot hitting a singularity is exactly like a basketball player locking their knees.
Because the motors cannot actually spin infinitely fast, the physical robot either violently jerks, violently vibrates, stalls out entirely, or the computer registers a massive fault and shuts the system down to prevent the arm from tearing itself apart.
Programming complex continuous paths is largely an exercise in recognizing where these invisible mathematical singularities hide in the workspace and meticulously routing the arm around them.
It is incredible to think that these massive, heavy steel machines are entirely beholden to the quirks of trigonometry. We have covered an immense amount of ground today, pulling the concept straight from Shilling's Fundamentals of Robotics.
We started with the economics, exploring why the automotive industry had to evolve from the rigid, incredibly expensive retooling of hard automation into the flexible, code-driven world of soft automation.
We examined the physical anatomy that makes that flexibility possible. We looked at the electric servos that act as the agile gymnasts of the factory floor.
The hydraulic systems leveraging fluid pressure to act as the heavy powerlifters, and the clever use of compressible air in pneumatic grippers to provide selective compliance and protect delicate parts.
We took those Revolute hinges and prismatic slides and built invisible 3D boundaries in the air. The massive Cartesian gantry cranes, the swinging cylindrical and spherical volumes, the anthropomorphic crescent reach of the articulated arm.
And of course, the brilliant horizontal swinging, vertical stabbing Scara robot, perfectly evolved for assembling the microchips in the device you're probably using to listen to this right now.
We confronted the reality of mechanical error. We distinguished between the high precision of the microscopic mathematical grid, the repeatability of gears dealing with backlash and thermal expansion.
and the crucial lack of true accuracy in a blind machine operating in an unpredictable factory environment.
And finally, we dove deep into the kinematics, the direct arm equations solving for position, the incredibly taxing inverse kinematics fighting through multiple solutions.
And the terrifying singularities where the Jacobian matrix collapses, forcing massive steel joints to attempt the mathematical impossibility of infinite speed.
For a high school student looking toward a future in engineering, the ultimate takeaway here shouldn't just be the facts about motors or joints. It is about the profound reality of mathematics.
When you sit in a classroom staring at a whiteboard covered in sine waves, cosines, algebraic matrices, and geometry, it is very easy to feel like those concepts are purely theoretical. But this deep dive proves they are not.
Those equations are the literal, physical language that commands the automated infrastructure of the modern world. They are the invisible gears turning inside the software that manufactures almost everything you touch.
The math is the magic that converts electricity into controlled physical intent.
But I want to leave you with one final thought to mull over. Throughout this entire breakdown, we have been describing machines operating in a purely mathematical, rigid universe.
The complex kinematic equations we discussed operate on a fundamental assumption. The robot calculates exactly where it is, and it assumes the target object is exactly where the code says it should be.
The robot is deaf, dumb, and blind. It simply executes the math.
Shilling touches upon the necessity for evolution at the very end of his definitions. He states that to achieve true accuracy in a chaotic, unpredictable real-world environment, a robot must eventually utilize feedback from external sensors.
It needs tactile arrays to feel, and most importantly, it needs machine vision to see. The rigid kinematics we decoded today are just the skeletal foundation.
So as you look forward to what's next in engineering, consider this collision. We have perfected the rigid inverse kinematics. We know how to move the steel.
But what happens to the definition of a robot when we pair those perfect, rigid mathematical equations with modern generative artificial intelligence and advanced spatial computer vision?
What happens when the arm doesn't just blindly execute pre-calculated trigonometric trajectories, but instead looks at a messy, unorganized table of parts, recognizes the chaos, calculates its own mathematical path on the fly,
And decides for itself how to flex its mental muscles? That intersection, where perfect math meets intelligent perception, is the true frontier. And figuring out how to build it is something for you to explore next.